Okay, so I'm going to address question 4 on the worksheet before question 1 because it's conceptually, it comes before. And then question 2 and 3 you should be able to do without any additional guidance from me on that. Okay, so in question 4, I'm going to make up like a different question that's similar. But you have this integral, and you have some number, some constant out here, and you have, actually, we're going to put it there. Sorry. You have a constant here, and then a function here, and then some constant here. Okay? So generically, when you have an integral, and you're going from some lower endpoint to some upper endpoint, so from P to Q. So the point is, if you're looking for, what this is equal to, you're allowed to split up this integral as follows. The first piece can go in an integral by itself, and the second piece can go in an integral by itself because it exhibits what's known as linearity. And by the same token, you can split out the a like this as a multiplier. So then you have this structure. Now we have another trick here. This here is just b times q minus p. Okay, so that you can calculate. So when you're done, all you have is this as a variable. So the a is known, and this whole mess is known. So this becomes your variable that you solve for. Okay, so that's the structure of that question. Okay, so the piece you need to understand for the core of question 1 is the fundamental theorem. And so I'm going to step through that and then give you some more general advice on how to use Python to reduce the mechanical task of calculating the answers to the other sections of the exercise. Okay, so first of all, what is the fundamental theorem saying? Okay, so this is saying if you have some function based off of an integral, and you like to think of the lower endpoint as being fixed and the upper endpoint as moving, if you call that whole mess capital F of x, that is equivalent to saying that the derivative of capital F is lowercase f. Okay, so let me talk about this in terms of money. Okay, this is your bank balance. This is a discrete version of this. So capital F is your bank balance, and this is a list, little f is a list of changes or deposits and withdrawals. And interest, but an interest payment would just be a deposit. Okay, so this is your list of deposits and withdrawals. And how does that relate to your bank balance? Well, if you had a spreadsheet, so I just totally made this up. Let's say I have a spreadsheet and I have a column of deposits, but I'm going to put the withdrawals in there too. So the negative number means it's a withdrawal. Okay, now the balance, usually you just assume you're opening it somewhere. You have some kind of opening balance, or if you had a previous balance, you put a line in there to say like your opening balance may have been 100, in which case this would have been 103. Okay, that's fine. That's your constant of integration. It's changing that opening balance, but it doesn't matter for our discussion. And then what we do is we just create a formula. You can do this. And I'm just going to say, is A3 plus B2, right? That's what I want. And it's just going to sum this up for me, hopefully. Okay, so my running balance is my accumulation. So think of the running balance as my accumulation, and the deposits are the changes. Okay, so these are changes, and this is accumulation. Okay, the accumulation is your capital F, and your changes are your little f. And so if you add up all the changes, that tells you the accumulation. And this C down here, this is my starting balance, and we often just start it at 0, but we could start it anywhere we want. That's just telling you how much, well, it's kind of telling you how much you started with, but not exactly. It's telling you the time at which you started, and then your capital F is going to change based on if you know that or not. Okay, so let's say if we had the balance, how would we figure out the deposit? Well, we would just do a subtraction. The only thing we can't figure out is if we start with the first balance, if we don't know what the opening balance was, we wouldn't know what the previous deposit was. But we can figure out everything beyond that. And that's exactly why we need a constant of integration. So when you go from the balance back to the deposit, you have to know that opening balance. And that's just, you can't get the process started, but you can know everything up to that one missing piece of information. Okay, so we have the ability to now take advantage of what we already know about derivatives in order to calculate integrals. So we can do some pretty ridiculous looking things. So let's say capital F is e to the sine of x. That means lowercase f would be cosine x e to the sine of x. So if we wanted to take the derivative of some disgusting mess inside the integral, sometimes we're lucky enough and we can reverse engineer the function that it came from. So if you have something, if you just randomly put stuff inside an integral, you're not very likely to be able to take it out. But if you design it with this in mind, knowing the rules that we learned how to take derivatives, we can very carefully undo the derivative. So this is a pedagogical point. I cannot just make up any old thing and ask you to integrate it. But if I carefully design it based on how we know to take derivatives, you can carefully dismantle it. Okay, so as you go up higher and higher in mathematics, this becomes more the case. When you're just learning how to add, your teacher could give you any two numbers and you could add them, or any two numbers and you can multiply, any two fractions and you could add them. And at some point you get up to calculus, which is where we are. And I cannot ask you to take the derivative of any function. I cannot ask you to take an integral, integrals being much harder than derivatives. So in differential equations, it is even more ridiculous. There's only a very small number of things we can manipulate. And so as a teacher, or pedagogically, we have to present you with only exercises we've carefully constructed that you are trained on how to solve. Okay, so don't let that disorient you. That's part of the process, and it just gets worse in diffie-Q. But that's a good thing, because that means there's a limit to what we can ask you. The other thing you will notice is that if I wanted to take the derivative of this guy, I could say d by dx, and that would be like, another way of saying it is just put a little prime sign outside some brackets, and that's going to be cosine t e to the sine t. And you may say, hey, wait a second. Now, first of all, I want to point out what the t is doing. T is your independent variable that is being used in integration. It is a temporary variable, and the function itself, we're talking about, I'm sorry, this should be an x. Okay, so be careful. Depending on what field of study you're in, there is a different amount of forgiveness for the care you take with your variables. Some people will say that you can do this sort of thing because it's obvious that this x is not this x, and it's not going to confuse anybody. And then there are mathematicians who say, no, 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 we will get confused by anything you do. So you have to use a different variable inside the integral. So you have to be aware of whether you're like in a physics environment or whether you're in a math environment to get your cues as to whether or not that kind of behavior is okay. All right, but what I do want you to notice is now you can ignore this guy and notice that this piece is the same as this piece, which means, okay, so now I've just changed things around on the screen a bit. So this whole block can be replaced with just a generic f of x. It doesn't have to be the same f we used earlier. I could use like a different variable if that makes you happy. It doesn't actually matter. The point is that it's the same, whatever that is the same as that. And the only difference is, in this case, we're in a math class, so we have to use a different variable. But as long as, like, it doesn't have to be a t either. It could be an s. It could be any variable as long as this matches this here. And then this guy, so this x in this case, matches this x and this x. That's how the variables have to match. Okay, and so that's the fundamental theorem. Okay, so one of the questions in exercise 1 is saying, using the fundamental theorem, compute an integral exactly. So how exactly do we do that? So we have to think back in terms of bank balance. So let's think about this. If we're being asked to calculate something from point time, I don't know, 4 to 7, whatever that means, and then there's some function, and we're going to call this little f x dx. What does this mean? This means we want to know the area under the curve from 4 to 7. Well, what does that mean? Well, this point, this area is the accumulation change. So this guy is f of x, and if you think back to your bank example, these are your deposits and your withdrawals, right? And you want to know the accumulation of the deposits and withdrawals over a time period. So you're saying maybe a certain month. You want to know how much, what is your net increase or decrease over the time period. And so back to our bank example, if you want to know the net increase between this time 4 and this time 7, if what we have is the balance, we don't have the list of deposits, but we have the balance. All you have to do is subtract your balance on day 7 from your balance on day 14, and you see that the total accumulation must have been whatever the difference is, so 9. Between day 4 and day 7, there's a total of 9, which is the same value you get if you add up those three deposits. So that if you see 5 minus 4 is 1, and add that to 8, and that's 9. So you can add up all your deposits and withdrawals during that period, or you can simply do a subtraction on your two bank balances to see how much it changed. Okay? Let me give you just another visceral example of that. So if you imagine people getting onto a bus, they start the bus empty. At stop number 1, 3 people get on. At stop number 2, a person gets off, and so forth. If you want to know how many people how many people got on and off net total change in the bus between stop 2 and 4, you can say, wait a minute, so I know how many people were on the bus at that given time, and so I know that there were 5 people on the bus, there were 2 people on the bus, so a net 3 came into the bus. And so how would we figure that out? Well, it's actually 5 minus 2 is 3, and that tells you that overall you ended up with 3 additional people on the bus versus what was at the end of stop 2. Now the reason we had to discount the 2 here is because we're actually doing a discrete problem here instead of a continuous problem. And so in calculus we're dealing with continuous variables, and we don't have to be very careful about the endpoints because we're dealing with infinitesimals anyway. So that's something we get for free when we're dealing with the infinite. So if you're doing a discrete version of this problem, you have to be a little more careful. And let me just re-evaluate what happened on our other example. So we had this situation. We wanted to know what happened between, I forget what it was, let's say day 4 and day 8. So then it's 26 minus 14 is going to give us 12, which should be equal to what happens if you add up all that. So let's see, 8 minus 4 is 4, plus 5 is 9, and 3 is 12. So it works out. Okay, so you just have to, when you're doing the discrete version of the problem, you disregard the balance on the first day because you're actually just considering the balance starting after the deposit's been made. Okay, so again, when you're dealing with calculus, that usually isn't an issue you have to consider, but since we're looking at the discrete version, we do. Okay, so this is a version of the fundamental theorem that you're going to want to use in order to actually get the mechanics to work out on this exercise. And so the point is, if you have a function and you know its derivative, Okay, and then again, this is your deposits and your withdrawals, and this is your balance. It's saying if you want to know the net effect of deposits and withdrawals in your bank between two time periods, between day A and day B, you can simply look at the bank balance on day B and subtract from the bank balance on day A. Again, we're dealing with the continuous version of the problem here, so we don't have to worry about the fact that in the discrete version, it's not actually the exact same day. Okay, got it? Okay, and you already know how to make Riemann sums, but I'm just gonna give you a little refresher on Python here. I'm just going to use Python at my computer for future demos, but you can still go to REPL. I actually encourage you, if you like Python, just go ahead and put it on your computer. It's easier than using REPL because in this environment, or if you use idle or something like that, just install any version of Python, it'll work. These are really basic exercises, so you may as well just have Python on your computer to save yourself the trouble. From math import star, so we've got our pi and our e and our sine and cosine and exp and natural log and all that stuff. Okay, and so let's say we have some function that we want to integrate. Again, I don't know what it is. I'm just going to make one up so it's not identical to your homework. Lambda means we're just going to make a quick function here, and I can go like cosine of square root of x, and that's something like I really don't want to type in cosine of square root of x and evaluate it 4 times. That's just a pain, right? And let's say I want to evaluate it at 0, 0.1, 0.2, wherever you want to evaluate it at. Actually, I'm going to try to keep the same notation that I did before. Don't worry about using x in your lambda function. It's just a dummy variable and it's not really used, so x wasn't used already. Okay, so here we have x and we want to evaluate f there. So what I've been doing is this kind of thing. For item in x, you need to put some spaces here. Python really cares about indentation. Okay, and then you've got your function bing, it's all evaluated, and you don't have to worry that you typed something in wrong because you can just kind of look and see what you did, and if you did it wrong, you fix it. So it's really wonderful about Python. And then if I don't want to sum them all up, maybe, well, if I do want to sum them up, I just go like that. What if I want to sum most of them up and I forget how the indexing works? Just kind of play around with it and say, okay, those are the ones I want to add up, because this actually means in Python add up item 0, 1, and 2, and you don't use the last element. So just always double check that you're adding up the things you want to add up, and then say, okay, those are the ones I wanted to add up. Or maybe I want to add up item 1 to the end. What is that? Yep, those are the ones I want to add up. Just double check. Just be lazy, but also be a little bit careful here. Because if you're not used to using Python, don't make any assumptions. Just double check that you know what you're adding up. Go ahead and add it up. And then, of course, you can multiply that by, you know, your delta H or whatever. Okay? So that's just to remind you how to wield Python for this type of exercise. Okay, and so what happens when I make these recordings is I'm sitting here looking at your homework and I'm thinking, okay, did I need to cover anything for you that you don't know already? And I think the answer is no. And I'm also looking at number 2 and thinking some of you are going to want help on number 2, and that's totally fine. I'm just not going to put it in the video because I want you to think more about it. And if you get it, you get it. And if you don't get it, we talk about it. So if you're confused, you come to office hours or you ask me in one of the breakout rooms in class. We're all here together. The videos are intended to hit the most common things that I think people need to hear. Okay, and sometimes I will leave concepts for you to struggle a little bit with, but that means I do want you to come to me and let me know if you need additional advice on that. Okay, see you very soon. Bye.